So when we left off our notes, we were talking about reactions between metals and nonmetals. I'm going to do a quick example here for those of you that only had that one day. If you don't think you need to watch this example, you can just skip ahead to the rest of the notes because we're going to talk a little bit more about ionic bonds, but also get into covalent bonding in these notes. So just skip ahead if you don't think you need this example, but I want to do reaction between aluminum and fluorine real quick. So again, remember, I'm supposed to know how to make Lewis structures for these things. Aluminum's in group 3, so it would have 3 valence electrons, and fluorine is in group 7, so it should have 7 valence electrons, right? 3 pairs, 1 single, whereas the aluminum has 3 single electrons. So again, there are 2 different ways to do this to show your work. I'll do them both, right? Aluminum is a metal, so it would lose electrons. If I want to show that the math way, I just subtract 3 electrons. That aluminum is empty then and has a +3 charge, because losing 3 negatives gives you more positives than negatives in that atom, so it's a +3 charge. Whereas the fluorine wants to gain 1 electron to end up full. And I'm going to draw fluorine is full over here. And now it's actually a fluoride ion with a -1 charge. So you're supposed to show your work, how do they become ions like that? But then realizing that they react together, it is going to take 3 fluorines to collect those 3 electrons that are lost by that aluminum. So I know that in the end here, I have 1 aluminum that's going to react with 3 fluorides. Sorry, you can hear my dogs barking in the background probably. Excuse me. And you're going to make, oh, and I also screwed up there. I was supposed to leave 1 dot unpaired, so let me fix that real quick. I had 3 fluorines to make 1 aluminum ion with a +3 charge and 3 fluoride ions. This time it needs to be full with 8 electrons. So again, that's just one way to show your work. I can also start out with my aluminum with 3 valence electrons and my fluorine. But then again, I do need you to use a different color, right? When you're doing work like this, I'm going to take these electrons from the aluminum and I'm going to move them to fluorines, right? And each time I do that, I can make 1 fluorine happy, but I'm going to have to keep adding fluorines until all of those electrons are gone from that aluminum. So I'm going to shortcut here real quick. I know I'm going to need 2 more fluorines. But essentially, as you do work like this, you just keep adding more of whatever it is that you need. If you have more to lose, add nonmetals to gain. If you need to gain, add more metals to lose. But overall, when you finish your work, you're going to have these 3 fluoride ions with a -1 charge, and you're going to have 1 aluminum with a +3 charge, and you're basically going to get the same result as we had below. So when it's all said and done, I still need you to give me this answer in that form, because that's what reactions look like, right? So I have to have one thing plus another with a reaction arrow gives me my products. So whichever work you choose to do doesn't really matter, but you still have to give me that same product when it's all said and done. So again, I kind of prefer to do the math method. You can do it whichever way you want, whatever makes you comfortable. But otherwise, we want to move on in our notes. And we're going to start talking about ionic bonds, compounds. We'll eventually get into covalent compounds with covalent bonding, right? But first, we just got to get a few definitions here. So I think you need to fill in that definition for an ionic bond. But essentially, when you have those metals and nonmetals reacting together, we make these ions we talked about. But then once you're done, that positively charged ion and that negatively charged ion, they're going to be attracted to each other. So when it's all said and done, if sodium and chlorine react together, they're going to end up forming those ions, a +1 sodium charge, a -1 chloride charge, excuse me, but they don't just separate at that point. Now that they're oppositely charged, they're actually attracted to each other, and that attraction is called an ionic bond. So now I have this ionic compound, right, that has this attraction between the positively and negatively charged ions. And ionic compounds, as it says below, we know that they're charged particles, and one of the unique things about those charged particles is they're going to conduct electricity, right, in two different situations. If they're dissolved in water and or if they're melted. It's a little hard to melt salt. It takes a pretty high temperature to do so. But if you can melt that salt and you have those ions that are free to move throughout a liquid, right, it can conduct electricity. It can be an electrolyte, right? I think you have to add electrolyte to your notes, so don't forget about this word right here. But more frequently occurring, right, when that salt is dissolved in water, which is very easy to do, you're also going to see that it's an electrolyte. So I can show you an example of this later so you can see what's an electrolyte, what's not an electrolyte. But obviously these notes are online. Can't really do that right now. But electrolytes can conduct electricity when dissolved in water or when they're melted, right? So ionic compounds are unique in that. Acids and bases can technically conduct electricity as well, but that's because they actually react to create ions in solution. So when we talk about acids and bases down the road, either way, right, acids are associated with a specific ion, a hydrogen ion. Bases are associated with a hydroxide ion, right? If you can create high ions in solution in water, it's going to be an electrolyte. So a few connections before we move on, right? First is this heavy metal toxicity, right, which kind of sounds like a rock band or something like that, but really I'm talking about like lead poisoning and mercury poisoning, things like that. So things like lead and mercury can actually bond to sulfur-containing groups and proteins, and that can actually hinder and or completely destroy that protein's ability to do whatever it's supposed to do. So it can actually kill cells. It can kill you if you had that kind of poisoning. It's not frequently occurring, but there are some specific scenarios you would look out for. So, I think it's like pre-50s paint. They used to use lead salts in those. And again, that's another thing that I can show you later, but online I'm a little bit limited. But lead salts are really colorful, right? Lead iodide is a really bright yellow color. And yellow is actually kind of a hard color to come by in nature to make a pigment for your paint that's going to last, that's not going to fade, right? So they used to use lead salts for that purpose, but then it turns out that it's possible that that lead can be ingested by someone and can hurt them, can poison them, right? One of the major things there is actually has to do with young children, right? Babies and their cribs possibly that have lead paint on them. That was kind of dangerous because, as you all are probably aware of, babies tend to put pretty much everything and anything in their mouth, and lead actually tastes sweet, right? And we are evolved to know that that sweet means nutritious and delicious, right? It means that there's something there that I need, right? So when we taste sweet, we think that that's something that we're supposed to be eating. And so babies can very easily start eating that lead paint and not know that it's a bad thing. And then they end up with that poisoning, right? Most of the time, though, otherwise, the reason why you would want to know that that lead paint is in your house or on that old barn or whatever it happens to be is because if you were working with it, if you were cutting through pieces of wood that were painted, right? You can still ingest the dust from working with things like that, and you could very easily get that poisoning in that case. So we're a little bit worried about that. You should always check if you have an old house, right? If you're in the process of buying a house, you would want to know if there's possibly any lead paint. It's actually pretty rare anymore, I think. But, if you buy something that's an antique, or right, maybe it's just been around in your family for a long period of time, right? It's possible that there's lead paint. You should make sure that you know that. Because again, you're that young child's not going to know any difference. They're just going to taste sweet and just eat away, right? Otherwise, mercury poisoning, right? You need organic compounds like methylmercury, right? It can't just be regular mercury. So there are some forms that are dangerous, other forms that are not necessarily as dangerous, but all mercury can be toxic. So you want to make sure that you're taking care of that. There's a reason why in my lab, in the chem lab here at school, I can't really use mercury thermometers. I'm not supposed to, at least. I have a few and I like them because they equilibrate very quickly. But when it's all said and done, if one of those breaks, it costs a lot of money to clean up that spill. So mercury is something that we worry about. Um, a lot of times, right, it's really pollution, it's runoff from factories that's the problem. So that's how that mercury can end up in the food web. And we've done a pretty good job of cleaning that up, but there are still some areas in the world that are underdeveloped and or they don't really regulate things the way that we do that can cause that mercury poisoning to happen in ecosystems. So if you got runoff in like Eastern Asia, right, around China or Japan, right, if you catch a fish in the ocean there's chances that there could be some mercury in that fish, and then you eat that fish and you go to a concept of forgetting what that term is. Maybe I'll think of it later and tell you guys. But as a toxin like mercury works its way up the food chain, typically, it builds up in each successive level of that food chain. So more and more of that toxin is collected. So if you're at the top of the food chain, it's going to hurt you worse than anything at the bottom of the food chain, right? Because it's called biomagnification. That's the word that I was trying to think of, right? So we actually may have learned that in biology, but I don't know. Maybe we didn't even get that far last year, so it depends, right? But it does tend to get more toxic as you work your way to the top. So since we are at the top of most food chains, we worry about that a lot more. There's also that electrolyte connection, because when I said electrolyte to begin with and you started writing that in your notes, you probably thought about that right away, thinking, oh, that's what it says on Gatorade, right? So electrolytes are found in your blood, in your interstitial fluid around your cells, and intracellular fluid inside of your cells, right? We would express those concentrations in these milliequivalents per liter, right? So they're really not highly concentrated, but they need to be there, right? You do have positive and negative ions. The concentration of those positive ions should balance out the concentration of those negative ions, so it's actually overall electrically neutral. But we use those electrolytes to create electrical potentials. It's how your body communicates, actually, right? Nerve impulses, right? Electrical potential across membranes, muscle contraction, all of those things are caused by ions moving across membranes in your cells, right? So that's how you signal your body to tell it to do something, right? And if you signal a muscle and tell it to contract, and then you can't signal it again to tell it to stop doing that, that's when you end up cramping, right? If you have an imbalance in electrolytes, right, that's what causes symptoms like cramping, right? So there are conditions from losing electrolytes. Again, If you lose a lot of electrolytes, you tend to have diarrhea, vomiting, kidney dysfunction, things like that. But you can treat it by IVs that contain electrolytes, right? You just get a basic IV there, right? Because every ID is going to have salt in it. So sodium chloride, you get that right away. But those sports drinks, they advertise the whole electrolyte thing. And yeah, they do have those electrolytes. And yeah, you lose some of those when you sweat. But really, you don't need those electrolytes as long as you have a normal diet, right? It's really, Gatorade was originally made for elite level athletes, right? Unless you're a pro and you're working eight plus hours a day, right? Working out and practicing whatever it is that you're doing, right? Unless you're working that hard, it's really unlikely that you can't just replace those electrolytes with your normal diet. So usually you don't have to worry about that, but in extreme scenarios, you may worry about that. So there are times when maybe it's exceptionally hot, right? And you've been sweating even more than normal, that maybe that Gatorade would be necessary. But even then, a lot of times it really doesn't matter. Just drink water. Probably in that Gatorade, the sugar would help you more than anything else when you're in competition. So just drink Kool-Aid. Otherwise, we're shifting here to covalent bonding. So when you have two atoms with similar tendencies to gain or lose electrons that come together, you're going to satisfy that octet rule by sharing those electrons instead of stealing, right? So if you have two nonmetals that come together, typically they would gain electrons from metals, but if there are no metals around, if you got two hydrogen atoms, both of which want another electron so they can be like helium, but if they don't have a metal to steal that electron from, they just share those two electrons. And that's what makes a covalent bond. I like to visualize covalent bonds as being a shared pair of electrons that are orbiting those two atoms in some kind of elliptical fashion like this, right? And what ends up happening is those two electrons that sometimes are over here on the left, sometimes over here on the right, as long as they're traveling around those two atoms, you have a link between those two atoms that holds them together. Right? I like to think of it as like a rope that's tying those two atoms together. Right? These covalent bonds are very strong attractions between these two atoms. Right? They both want those electrons really bad, so they fight to hold on to them. Right? Whereas when we were talking about an ionic bond not that long ago, right? If I had a sodium, pen's being weird again. If I had a sodium ion, and then I made a hydride ion, because the hydrogen would steal an electron from that sodium, there's still an attraction between these two atoms, but that attraction is much smaller than it was between those two hydrogens above. A covalent bond is much stronger than that ionic bond. The ionic bond is an attraction between that positive and negative, but as long as two atoms are sharing electrons, they're tied together, right? It's a much stronger bond between those two things. So then you have that next definition, molecules. Once you have covalent bonds, you can make those molecules. Some molecules are diatomic, meaning they contain only two atoms, That's what di meant, right? Two atoms, diatomic. There are some specific diatomic molecules that I need you to remember. As we work in the future, hydrogen tends to be diatomic. Nitrogen tends to be diatomic. Oxygen tends to be diatomic. And all halogens tend to be diatomic. Right? When I use an X to generically represent an element, I usually mean halogens. So those are those things in group 17 and group 7A, the fluorine, chlorine, bromine, iodine, those elements. So all of those would end up being diatomic as well, right? They tend to form these molecules because they can work together, two atoms of that same element, to share electrons and both be happy to satisfy your octet rule. Right? Molecular compounds are compounds that are made up of molecules, and only molecules. Most do not contain ions and do not conduct electricity, and therefore are non-electrolytes. Right? The only exception of a molecule that can be an electrolyte are those acids and bases again. Right? So we'll talk about those later, but most molecular compounds are non-electrolytes. Okay, covalent bonding. You can have more than one pair of electrons. Again, when I had the hydrogen example from before, you're sharing one pair of electrons, but that could also work for those halogen examples, right? One fluorine and another, they both want one more electron to make that octet rule satisfied, so they share a pair of electrons between the two, and then both atoms get to be happy at any given time, right? You can also have double bonds, right? Oxygen, again, diatomic. It's diatomic because each atom has two single electrons, and each of those single electrons can be used to make a pair of electrons to make a covalent bond. So there would be a double bond between these two oxygens at this point, right? And a triple bond, that's like my nitrogen example, right? Nitrogen has three single electrons, being in group 5. So it can make 3 different bonds sharing pairs of electrons, and it can make 3 bonds with another nitrogen. So these 3 examples, you see a single, a double, and a triple bond. You should be able to form bonds between atoms, right, in a similar fashion. So at this point, we get to the crux of this, right? We're going to practice some things that are going to be on that worksheet that I gave you before, that I gave you Friday, right? So when you have nonmetals that come together, you need to know how they're going to react, and you need to be able to predict what kind of products are going to be made, right? What's going to end up forming as a result. So I have 2 hydrogens and an oxygen, right? So what I'm supposed to do when I'm given a prompt like this, I was not given a metal, so I'm not going to make ions. But if I give you nonmetals like hydrogen and oxygen, you should be able to make a molecule out of it. And all the time, these are always going to be simple molecules, relatively simple. More complex molecules would be a little bit harder to predict. But essentially, if you work through this by trial and error, there's no way that you're going to end up with the wrong answer. Right? You might not get it right at first, but you just have to keep trying in different ways, and eventually you're going to get all of those atoms to be satisfied, all of them to share electrons to make bonds. And it's pretty simple, actually, right? And this is where that idea of moving electrons before and using that visual form of work to create your ions might actually be hurting you a little bit, because this is going to look similar, but it's not actually the same thing, right? So make sure that you can differentiate when it's all said and done. So I have an oxygen here that has 2 pairs and 2 singles, so every oxygen always makes 2 bonds, or should make 2 bonds, whereas these hydrogens are only going to make 1 bond. So all I need to do to make a molecule is connect singles to make pairs, right? So it's actually fairly simple. I just find a single, I connect it to another single, that's a covalent bond, right? I find a single here, I connect it to another single electron, that's another covalent bond. Now you have a molecule. Specifically, this is a water molecule. So it's really not super difficult. Most of the time it's pretty intuitive how you're going to do this. Generally speaking, you want to put the atom that can make the most bonds in a central location and work your way out from there. Because my next example, I'm going to have a carbon and 2 oxygens. So I need to figure out how those things can be connected together. Now, the carbon is in group 4, so it should be able to make 4 bonds. So I'm definitely going to put my carbon in the middle. it can make more bonds than oxygen. So I'll put my oxygens on either side. Well, excuse me. And from there, figure out how to connect my dots. So again, when we were doing the metals and non-metals, if you were doing this kind of work, something that looks similar to this, you had arrows, you were using a different color, you were representing those electrons moving from one thing to another. This should not be confused with that, right? I'm not actually losing an electron when I'm talking about this oxygen and connecting a dot to this carbon, right? I'm sharing electrons between those two atoms. I've created a covalent bond between those two things. So I'm not losing anything. There is no arrow. There is no, right, new electron that's now permanently around that carbon. Sometimes it's around the carbon, sometimes it's around that oxygen. So you need to understand the difference. But then I'll connect another single to a single, right? And then I only have two left over here. I'm going to connect this single to that one. That was kind of goofy. And then that last one there. Sometimes if it looks kind of funky the way I just made it, right? If you have those double bonds, I'm going to clean that up a little bit. And I still have pairs of electrons around this oxygen, 2 pairs of electrons. But I'm going to end up with this molecule here with 2 double bonds to 2 different oxygens from that carbon, and that's carbon dioxide, right? So you should be able to take atoms and connect them together and figure out what it would look like, right? And there's really no other way that you could have connected these things together to make every atom satisfy the octet rule. This is the only way that it works. So like I said, trial and error. Simple trial and error will get you your answer every time. Okay, one more example, one last example, and then we're done with the notes here. Before you continue watching here, you might want to try and predict this one on your own. This one's actually a little bit tougher. So I have a carbon and I have 2 hydrogens and I have an oxygen. So I would like you to pause the video right now and then try to build this on your own and then just start the video back up and see if you did it right. It might take you a couple tries, but if you just work at it and just keep connecting things to whatever you need to connect them to, you should be able to figure out how to make this work, right? So again, if you just paused and unpaused, hopefully you did try to do this on your own first. I'm going to take a carbon, put it in the middle because it makes the most bonds, and then I'll just put the other atoms around it. And when it's all said and done, right, everything essentially gets connected to this carbon in the middle, right? I just need to start connecting all of these singles together, and you should end up making a molecule that looks something like this. If I clean that up, I got a double bond to an oxygen, I got 2 single bonds to hydrogens. This molecule is a formaldehyde molecule. Right? I think you've heard of that before. It's an embalming fluid, right? It preserves dead living things. So chances are that might have taken a couple tries to do that. Maybe you got it on the first shot, and that's great. But some of these examples are a little harder than others. It depends on the example. Right? And there are even a few examples here and there that I might give you that could have more than one answer, right? But most of the time, if you just continue to work at it and start over from scratch, right? If it doesn't work the first time, just try again. But generally speaking, if you put the thing that has makes the most bonds in the middle, you're going to get the answer that you want. Right? One thing that somebody may have done, right? It's possible that you connected a carbon to the oxygen and then tried to connect the oxygen to a hydrogen. Right? The trouble is that you're never going to make everything happy doing that, right? So I could do that, but then I have these 3 pairs left on, or 3 singles left on a carbon and only 1 hydrogen to occupy those things, right? So the carbon can't bond with itself. That's never going to work. So just make sure, again, you put the thing with the most bonds in the middle and work your way out, right? So this work up here got me the answer that I wanted, but if I tried to put the oxygen in the middle, it's not going to work, right? So just trial and error, get it figured out. Otherwise, that's it for these notes. You'll have some extra practice in class Monday to work on.